Alright, in 4.2 we have several ideas that are being brought up. They're going to talk to us about or probability as well as and probability. And so they call them the addition rule and multiplication rule. I'd like to steer you away from the rules themselves and just get you to think intrinsically about them. The first thing that they're going to do though is somewhat of a review from the old stuff. They're going to look at not probability, which we brought up in the last video, the probability that an event does not happen. And so they're going to harp on that here. So it says a certain group of women has a 0.22% rate of red-green color blindness. If a woman is randomly selected, what is the probability that she does not have red-green color blindness? And so I chose this problem pretty specifically because it was in the homework and it has a high potential of a small mistake. So let's take a look at the probability that a woman has red-green color blindness. They just give it to us. So if they ever give you a percentage, percentages and probabilities are theoretically the same thing, except probabilities are always the real number equivalent. So remember that the percentage was 0.22%. That means the probability is 0.0022. Remember that to change something to a percentage, so if I have 5%, that translates out to 0.05. I move the decimal point back twice. Well, think about that for 0.22%. You got to change it to its real number equivalent. You got to move that back twice, and hence my 0.0022. The mistake sometimes is for people to say that the probability that they have red-green color blindness is 0.22. It's not. It's 0.0022, and they're asking for probability. And so we want the probability that she does not have red-green color blindness. And so what is that? Simply 1 minus the 0.0022, right? If I told you that 60% of the student body at Folsom Lake College was female, you would know that 40% is male, simply by doing a 1 minus or 100% minus. The ones like our 100% minus 0.0022, and the answer we should be typing in is 0.9978. Not surprisingly, 99.78% of the women should not have red-green color blindness. And so you'll have questions like that. What's happening in this area, because they need to get to the next stage, which is what I mentioned earlier, or probability. And or probability is best done through a chart. And so our author likes and uses a lot test results. So we're going to look at one of the problems that's in the homework, or at least reference-wise, and that is a lie detector results. And so what's going to happen in a lot of the problems in the homework in this section and the following is they're going to be given in a way where they have charts, and so where the information is summarized in a table. So we're going to look at having positive test results and negative test results. Now what happens with the lie detector is it's not very accurate. In fact, no test is completely accurate. And so what we are doing is testing the test. So what they have written up here is did not lie. Now if somebody did not lie, they should get a negative test result. And 32 people who did not lie got that negative test result. But 15 did. 15 got a positive test result. They call these guys right here false positives. So if they use the word false positive in the book, and I think they will, that means you got a positive result when you shouldn't have. If somebody's not lying, the polygraph should say a negative test result. And it did for 32 of the people, but for 15 of them, it was a false positive. Now, the other thing that's happening is the people are lying as they do this. And that's what the lie detectors geared to do is pick up the liars. They caught 42 people who were lying. They lied, and the test said that they lied. But as you know, it's also going to be wrong sometimes. These are the false negatives. They got a negative test result, and that was not true. The 9 people were lying. So you want to take some time to talk about who these people are. So if I go and highlight a few, 42. Who are these 42 people? They lied, and the test said that they did. And the test reflected that. Who are these 9 people right down here? They lied, and the test said they didn't. And take some time to just understand the information before you start answering questions, because everything related to probability is your ability to understand the situation. And so let's go answer some questions. So they're going to ask some questions from 4.1 and others. They're going to ask this: if one person is randomly selected from this group, find the probability that they lied. And that's a 4.1 question. There was no or in there or anything. And so we're going to take this 4.1 question and just answer it. The probability that they lied would be the number of people that lied. How many liars do we have? Well, please don't mistake a positive test result with actually lying. The actual liars are right here. Those are the people who for sure lied. 42 of them got caught, 9 of them didn't. These other 15 that got positive test results, they're not liars. The test just thinks they are. And that's going to happen from time to time. Super frustrating, right? But it happens. And that's why lie detectors are thrown out so often, is because they're wrong a lot of the times. And so out of that, all we have to do is know the number of people who lied. It looks like there's 51 who lied out of the total number of people who took the test or who were involved in the study. If we take the 15, the 32, and the 42, and the 9, let's add them up. 15 plus 32 plus 42 plus 9. That would be the total number of people. 98 people were involved in this survey. Sometimes they tell us that. We're done. 51 over 98 is our answer. That is the probability that somebody lied. What's the probability that somebody tested positive? Well, let's go do that. That's another 4-1 question. Sorry, we'll keep that 98 because that helps us out a lot. Well, I know that there's 98 people. How many tested positive? Let's go find out. These guys right here tested positive. The 15 and the 42. So what's that? 57? So we come in here and we write our answer of 57 over 98. And we're moving on. So they're going to ask some questions that get you to understand that. Now, what makes this section unique is something like this. This question right here. So if you're okay, I'm going to erase these guys right here and ask another one. Find the probability that, and here's what it's going to say. I'll put it in a different color for the new section, that the person lied or tested positive. Now, they're going to tell you a formula for this, but don't use the formula. The formula is crazy. Just think about it. It's a simple question. One person's being selected, so we're going to have one fraction. We need them to either have lied or had a positive test result. How many people are there? 98. 98 total people I could select. So picture it as a bunch of paperwork. One for every person. There's 98 pieces of paper out there. I could have one of any 98 picks. And I'm going to select one of them. What is the probability that that one selection is somebody that lied? Well, here's my liars. right there. I already got 51 people. Is there anybody else that I have not highlighted already that needs to be included? So let me come in here and put a big blue check mark right through the light. I just handled all the liars with that highlighting that's there. I got to tack on these 15 other people. So it is the 42, the 9, and the 15. So let me emphasize that by saying it's 42 plus 9 plus 15. Here are my liars, and here's the additional people that did not lie, but the test said that they did. My additional positive. So I'm not counting the 42 twice. So I got 42 plus 9 plus 15, and I'm looking at 66 over 98. Now that can be reduced, so let's practice with that, because they probably have to have it reduced for the computer. And 98 divided by 2, 49. And that looks good. 49 is just made up of a couple of 7s, so we know we're done at that stage, because 33 is a 3 and 11. No 7s involved there. So OR just says, hey, tack on what you need to. And so they're going to give these types of charts, and our job is to understand them. At times, though, they're going to give us information in order to they're going to give us information, and we've got to create our own chart. So here's one for a drug use chart. The following results are from a marijuana drug test. Among 143 subjects with a positive test result, 24 are false positives. Among 157 negative results, there were 2 false negatives. Now, where did I get this? Straight from the homework, and it's there a couple of times at least. So what do we have to do? Pretty much like we did before. A positive test result and negative test result. Used marijuana, did not use. Okay, so drug tests aren't perfect either. So what do we know for the following results? Among 143 subjects with positive test results, 24 were false positives. Now, a positive test result is supposed to tell us that somebody used. So this is our false positive area, and we put our 24 there. Now, how am I going to get the other one? This is going to be 143 minus 24. And or 119. So come in here and replace that with 119. So again, what we did is we said 143 subjects with positive test results. That's our first row. 24 were false positives. You get a false positive when the test says that you've used it by giving you a positive, but you did not use it. And then on the bottom, among 157 negative results, 2 were false negatives. So the 2 were right here, and the other 155 are right there. So let's see how many people are involved in this study. 119 plus 24 plus 2 plus 155, 300. So we've got 300 total. That'll help us to get some probabilities out. And so they'll ask some questions based upon that, but they're going to have you come up with this. So hopefully we're okay. They will be using this terminology, false positive, false negative. 24 were false positives, so the other 119 amongst the 143 were perfect. They were true positives. And these 2 down here, right here is where I'm looking, they are false negatives. So let's talk about these people. Okay, picture these as individuals who were screened for employment for marijuana usage. Who are these 2 people right here? Let's describe them. Well, who are these 155? Let's start at the bottom corner. These are 155 people who did not smoke marijuana, and the test confirmed that. So they're happy. They are vindicated, right? Who are these 2 people? Right here, if I just go around. These 2 people actually used marijuana, but the test didn't pick it up. So these 2 people are very happy because they're not going to lose employment even though they've been using marijuana. So these 2 people kind of got off. They're using, but the test doesn't pick that up. These 119 people, they used marijuana, and the test confirmed that. So these individuals are not, they're upset that they got caught, but they're not surprised at all because it's what the test should have done. So who are these 24 people? These 24 people are mad people. These 24 people have not used marijuana whatsoever, but the test is telling the employer that they did. These 24 people are being withheld employment because of a drug test giving a false positive, right? Saying that they used them when they really didn't. And so they should ask for another test. And so that's what using a different testing mechanism would be ideal. So we use the information given to give this. So we could ask this question. Find the probability that a randomly selected person from this group used marijuana or tested positive. And they're going to feel exactly the same. So we already know our bottom number. So used or positive, our bottom number is 300 because we're going out of the 300 people. Let's go find the ones that used. I need to get these 121 people. And additional positives, 24 more. So I got to take the 119, add the 2, and add the 24. Notice we're not double counting anybody. And so we have 119 plus 2 plus 24, and it's that easy, 145 out of 300. They probably will expect us to reduce that, so we know both are divisible by 5 at least. Yeah, if I divide 145 by 5, I get 29. 300 divided by 5, you probably already knew is 60, and that's good. So about half of the population, a little bit less, would fall into that category. That's not surprising. There were 300 people total, and we didn't count 155 of them. That's a little bit more than half. So yeah, we have a little bit underneath half coming through there. If we wanted to express that as a decimal, we would just divide the two numbers and do 29 divided by 60 and come up with 0.483. As a rounded off value is 483 repeating. So that's the style of work that's going to be here. You're going to work with charts and other things like that. So the last group of problems, maybe I can still use this chart, is going to be what I call multiple selections. Some will call it and probability, but that gets a little bit confusing. So what's going to happen here is, let me recreate this chart that's here, or maybe even move to a different one that they use. And they do use a lot of charts. Looking in our book really quick for a different chart that they are using. Oh, apologize, I'm in the wrong book. That's why I'm not finding what I want. But I just wanted to give some homework styles of examples. So here's one that they have, and I'll try to put it out here as quickly as possible. Accurate, not accurate. And we have McDonald's, 329.33, Burger King, 264.54, Wendy's, 249.31, and Taco Bell, 145.13. So what this is these are drive-through orders, and whether the orders were accurate or not. And so they're going to ask us this type of question. Now they can still ask us the or probabilities, but I'm going to go to the and probabilities. They would say something like this: if we randomly selected three orders, find the probability that all three orders came from McDonald's. Okay, so the way we handle this type of situation is one at a time. So I want the probability the first one's from McDonald's, and then the next one's from McDonald's, and then the last one's from McDonald's. Okay, one at a time. And so let's talk about that. We're going to go into this group, and this group, let's figure out how many people are in this group. I don't think that they told us in the problem. So this is 329 plus 33 plus 264 plus 54 plus 249 plus 31 plus 145 plus 13. 1,118. So I'm having 1,118 orders. So some of those, just going to add it up really quickly again. Yeah, I got the same thing going backwards. So there's 1,118 orders. So when we first go in, there are 1,118 orders, and we want the order to be from McDonald's. So how many are from McDonald's? Well, 39 plus 33 are from McDonald's for 362. There's 362 orders that are from McDonald's. Where are they? Let's make sure we see them. They're right here. Those are the 362 orders. Now, we got that order, and we want to go get another order. There's 1,117 orders left, out of which 361 are from McDonald's, because we lost, as we selected that first order, picture that paper coming off, we lost one of the orders, and we lost one person from McDonald's. And then the last one is there's 360 orders left from McDonald's over 1,116. So let's play this scenario a little bit more. So with the first one, I think you see the 362 over 1,118. It's highlighted. Now what happened? We stole an order away. Maybe we took one of these away, and now there's only 32 there. Now I'm down to 1,117 and 361 orders from McDonald's. What happened then? Well, I took another order, and so maybe it could have come from the accurate ones, but maybe it came from the non-accurate ones. So actually, let me make that more clear. But you're losing an order every time. So remember, this was 32 under here, but maybe we took one from the accurate orders up here, and this is 328. Now I'm down to 360 out of 1,116. You're going to put this in your calculator by taking 362 divided by 1118 times 361 divided by 1117 times 360 divided by 1116. And you're going to come up with an answer of, and let me put that answer in black, an answer of 0.03375, so 0.0338 would be out to 3 significant digits. So would it be unlikely to select 3 orders and have them all come from McDonald's? Yes, under 5%. And so they may still ask those types of questions. And so that's what we're dealing with these types of questions. We're just thinking about the situations. So if I told you that in our class there are 15 women and 10 men, if 4 people are randomly selected from the class, what is the probability that they are all men? Right? And so that could be the question. So what you'll see is that you're picking more than one person. With more than one person comes a fraction for each person. So I want the probability that they're all men. So what does that mean? I need the first one to be a man, and then the second one to be a man, and then the third one to be a man, and then the fourth one. So everyone is represented by a fraction, and you're timesing them all. So let's go into this group. When you first go into this group, how many men are there? There's 10 men, right? So let me just make sure you see this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 men and 15 women. So there's a total of 25 people, 10 of which are men. So these 10 right here are all men out of 25 total people you could have picked. Okay, you have that man. So their notation for that is the the probability that an event happens given another event has already occurred. So they'll use that notation. This means the probability of B happening given A happened. So the thought process is, hey, let's go in and get a man. Okay, we got a man. So that's got to be what you think, that we got a man. So let's go get a man. So you want to you want to picture one of the men dropping out. Now, how many people are left in the room to pick from? Now only 24. How many of which are men? Only 9 are now men. You can see it right there. That took place. So we are given that the first two things took place. How many people are left? 23. How many men? 8. Where are they? 1, 2, 3, 4, 5, 6, 7, 8. Okay, that event took place. And you can see you're dropping 1 every time. It doesn't have to happen. They could be independent from one another, but it often happens. And you have that type of feel. And so you can take 10 divided by 25 times 9 divided by 24 times 8 divided by 23 times 7 divided by 22 and realize that that's a super unlikely event to happen. If that happened, you would think that there's a bias towards selecting men. It's definitely not happening at random. If that was happening on at least a regular basis, it has a slight possibility of happening, but if it happened more than once, you'd want to look into how their selection process was going and who's involved, because there does seem to be some gender bias there. So hopefully that makes sense. You could have a situation like this. The probability that an alarm clock fails is 5%. Actually, if I'm going to word it as the probability, let me put it as 0.05, right? So if an alarm clock has a probability of failing of 0.05, it's going to fail. 5% of the ones that are made are going to fail at some point. So then they'll ask this question: what if you had 2 such alarm clocks? What is the probability? They both fail. Well, no problem. You need the first one to fail and then the next one to fail. The probability that the first one fails is given as 0.05, and the second one's just like it and not affected by it. And so it's 0.05 as well. So if the probabilities are given to you as percentages or as numbers like this, you can just let it ride. But that first and second alarm clock failing should not affect the other. So that's what we would have, and we'd have 0.0025 as the result there, right? If I multiply those two together, yeah, 0.0025, very unlikely to happen. So what's the probability then that somebody wakes up? Well, the only way that you're going to wake up, the only way you're not going to wake up is if both alarm clocks fail. So the probability that you're going to wake up is the opposite of them both failing. and that is 1 minus 0.0025. So you have a 99.25% chance of waking up, or a 0.9925 probability that you're going to wake up if you set 2 alarm clocks that have that type of fail rate. So just something to think about. The My Math Lab should provide you other great examples as well. So try the homework. Let me know what are the sticking points. But that's everything I noted in the homework, those types of problems. So hopefully you can refer here and refer to the stuff on My Math Lab and be well supported. But reach out to me if I can provide additional support.